The nuclear atom. The model of the atom in the days of Newton was a tiny, hard, indestructible sphere. Although this model was a good basis for the kinetic theory of gases, new models had to be devised when later experiments revealed the electronic nature of atoms. We now discuss how our modern view of the atom developed. Thanks in advance for watching this video. If you liked this video, don't forget to like and subscribe to the channel and activate the bell. It is very important for the continuity of this channel. By the late 19th century, electron and radioactive discoveries seemed to indicate that atoms contained negatively charged particles and were not indivisible as previously thought. Scientists sought to understand how particles are organized within an atom. In 1897, Thomson proposed that the atom looked like a plum pudding. In his theory, the idea was that atoms were made up of a ball of positive charge, called pudding, with electrons called plums dotted around inside it. Look at the diagram. In 1905, Rutherford and his two students, Geiger and Marsden, did an experiment to test the plum pudding model. They directed a beam of alpha particles at a very thin gold leaf suspended in a vacuum. Alpha particles are a form of nuclear radiation with a large positive charge. Look at the diagram. If the plum pudding model had been correct, then all of the fast, highly charged alpha particles would have straight through undeflected. Based on Thomson's plum pudding model, Rutherford predicted that most of the alpha particles would pass straight through the gold foil. This is because the positive charge in the plum pudding model was assumed to be spread out throughout the entire volume of the atom. Therefore, the electric field from the positively charged soap would be too weak to significantly affect the path of the relatively massive and fast-moving alpha particles. The scientists were very surprised when they discovered that although most of them traveled through the foil without any noticeable change of direction, a small number of alpha particles were deflected by large angles as they passed through the foil, and a very small number of the alpha particles bounced back. In 1811, Ernest Rutherford proposed a nuclear model of the atom to explain these results. Because the vast majority of the alpha particles had passed through the gold, he reasoned that most of the atom was empty space. Look at the figure. As a small fraction of the alpha particles were deflected, they must have experienced a powerful force within the atom. He concluded that all of the positive charge of the atom must be concentrated in a very small space in the atom's interior. So the positive charge of the alpha particle and the positive charge of the atom repelled each other, causing a small deflection. A very small number of alpha particles were even redirected back toward the source. Then Rutherford proposed the positive charge must be localized over a very tiny volume of the atom, which also contains most of the atom's mass, which he called the nucleus. Rutherford suggested that the atom is made up of a very small positively charged nucleus, which is surrounded by electrons that are negatively charged. His idea was that the electrons orbit around the nucleus in the same way that planets orbit around the Sun. In 1913, Niels Bohr adapted Ernest Rutherford's nuclear model suggested a model of the atom in which electrons move around the nucleus in circular orbits. Bohr did calculations that led him to suggest that electrons orbit the nucleus in shells. The shells are at certain distance from the nucleus. Further experiments led to the idea that the nucleus contained small particles called protons. Each proton has a small amount of positive charge and some of the nuclear mass. However, there was still a difference between the atomic number of the atom and the atomic mass. Bohr proposed the existence of a particle with no charge but the same size as a proton to keep the nucleus stable and to make up the mass. In 1932, James Chadwick was able to prove its existence. These particles are called neutrons. Rutherford's nuclear model of the atom was a major step toward how we view the atom today. It was not, however, a complete model and presented some major problems. According to the Rutherford model, electrons orbit the nucleus, and since their paths are curved, the electrons undergo a centripetal acceleration. Hence, they should give off light like any other accelerating electric charge. Since light carries off energy and energy is conserved, the electrons on energy must decrease to compensate. Hence, electrons would be expected to spiral into the nucleus. As they spiraled inward, their frequency would increase in a short time, and so too would the frequency of the light emitted. This process leads to a rapid collapse of the atom as the electron spirals into the nucleus, but we know that atoms in general are stable because there is stable matter all around us. Beyond that, this model predicts that light of a continuous range of frequencies will be emitted, whereas experiments show that atoms emit certain discrete characteristic frequencies of electromagnetic radiation and no others. Clearly, some sort of modification was needed in this model, and Niels Bohr provided it in a model that explained both the stability of atoms and their discrete characteristic frequencies of electromagnetic radiation. Although the Bohr model has been superseded, it did provide a crucial stepping stone to our present understanding, and some aspects of the Bohr model are still useful today. So we examine it in detail in the next video.